30th lecture, and we discuss some further properties of Z transforms in this lecture. We first recall that the Z transform is a linear operation, linearity. That is, if x1 and 2 of n have the Z transforms capital X 1 2 of Z with ROCs as R1 and R2, then multiplying x1 by an arbitrary constant A and x2 by an arbitrary constant B shall lead to A capital X1 plus B capital X2 with R, which is the intersection of R1 and R2, and with a qualification at least. And we said qualitatively that the Z transform is a wide-hearted operation. Or did we use this term in the case of Laplace? We did? Yes, sir. Okay. Z transform has the same wide-heartedness as Laplace transforms. To illustrate this property, we take a trivial example. A trivial example. If we have a to the n, un, the what is the Fourier? What is the Z transform? 1 by 1 minus a Z inverse, and the ROC is mod Z greater than a. All right. Let's take another a to the n u of n minus 1. Then what is the Fourier transform? I am sorry, the Z transform. It is the same thing, minus 1. Only one sample is missing here. That sample has a value 1. So what we have is 1 by 1 minus a Z inverse minus 1. Is that okay? The ROC is the same, mod Z greater than a. Now if I subtract this, pardon me? In mod, yes, because a could be positive, negative, or complex. All right. Now if I subtract one from the other, if I subtract this from this, what do we get? We get a single sample at n equal to 0, and the value is 1, and therefore it becomes a delta n. And therefore in terms of Z transforms, we have to subtract this, and the Z transform of delta n is 1. What happens to the ROC? ROC is all Z. You see, the ROC is at least this intersection, which means mod Z greater than mod A, but because of superposition the ROC has become wider. It includes the complete Z plane. Well, this is sufficient to demonstrate that the Z transform is indeed a wide-hearted operation. Next we consider time shifting. That is, if x of n has the pair capital X of Z, then x of n minus n0 has Z to the minus excuse me, Z to the minus n0 capital X of Z. Now the proof is elementary. That is, what we have is summation x of n minus n0 Z to the minus n, in which we make a change of variable, we put this equal to r, therefore we get x of r, then Z to the, well, n shall be equal to r plus n0, and therefore Z to the minus r, Z to the minus n0, and this is what comes out of the bracket. The rest of it is capital X sub Z. The proof is elementary, but several points have to be noted. That is, if capital X of n has the ROC, ROC is R, then the transform of Z x of n minus n0, that is the delayed or advanced sequence, is also R except for the point at the origin, which may have to be qualified because you are multiplying by Z to the minus n0. Let us look at this a little carefully. One often makes a mistake in this. We have said capital X of n minus n0 is z to the minus n0 capital X sub z. Suppose n0, well, capital X sub z ROC we denote by R, ROC is R. Then we are interested in the ROC of the whole thing, that is z to the minus n0 R. The ROC obviously is R if n0 is equal to 0, all right, if n0 equal to 0, that is there is no shift, that is a trivial result. However, if n0 is greater than 0, if n0 is a positive integer, then you see capital X sub z divided by z to the power n0, and if capital N0 is greater than 0, obviously you are creating poles at z equal to 0, and therefore the ROC of this shall be R minus, if R includes the origin, then you have to exclude the origin from the revised or modified region of convergence. One has to be careful about this. One can't say this very definitely unless you know what is capital X sub z. For example, capital X sub z might have some zeros at the origin, might have the same number of zeros, and therefore one has to be very careful about locating, about specifying the ROC of the shifted sequence. The origin may or may not be in the ROC. Even if the origin was in the ROC of the original sequence, the shifted sequence may or may not have the origin as origin in the region of convergence. On the other hand, you see if n0 is less than 0, capital X of n minus n0 X sub z, z to the minus n0. If n0 is less than 0, that is a negative integer, then obviously you are creating zeros at the origin. Now zeros at the origin are permitted, but if there are zeros at the origin, then obviously there will be poles at infinity, and then it is the infinity point or the infinite region that you have to bother about. That region may or may not be in the ROC depending on the nature of X sub z. It is not necessary that the infinity has to be excluded, because the pole at infinity may be cancelled by some zeros of X sub z. If X sub z has zeros at the origin, they might cancel. Pole zero cancellation might still keep the point at infinity, z equal to infinity, in the ROC. One has to be careful about this.
Sir, there is one more thing.
Yes.
We might be cancelling off some poles at z is equal to 0.
That is right. That is what I was saying. If n0 is negative, then obviously what we have is, let's say n0 is minus 2. Then we have capital X sub z times z squared. We are creating poles at infinity. Now there may be poles, there may be zeros at infinity of X sub z. Then they will cancel each other.
No, but poles at z is equal to 0 will cancel with z squared. Suppose
yes, could be. Yeah. So the whole function is modified, and one has to be careful about specifying the ROC. That's the only care that one has to take in a shifted sequence. Then we say this was time shift. Suppose we shift in the frequency, which means that if x of n is the pair of capital X sub z, then we multiply x of n by a complex exponential, let's say e to the j omega naught n x of n. Then obviously what happens is summation x of n e to the j omega naught n z to the minus n. This can be written as x of n e to the minus j omega naught z whole to the power minus n. So instead of z, we have z multiplied by e to the minus j omega naught, which means that this would be equal to capital X of z e to the minus j omega naught. All right. We will come to ROC a little later, but you see all that happens in this is that the frequency variable z gets rotated. Suppose z was r e to the j omega, then this argument becomes r e to the j omega minus omega naught, and therefore the angle, the vector gets rotated in the clockwise direction by an amount omega naught, and therefore this stands for rotation. If so, what happens to the ROC? It doesn't change, because ROC depends on the distance from the origin, not on the angle, and therefore the ROC of this is the same as r if the ROC of this is r. There is no change. The angle rotation does not affect the region of convergence. This is called multiplying by a complex exponential is the process of modulation, and therefore x of n is being modulated by the complex exponential. Actually it's a multiplier. Actually one doesn't multiply by a complex exponential, or multiplies by cosine or sine, which is a sum of two exponentials. And what happens in the Z transform is a rotation, a simple rotation. Now in general this could be generalized by saying, instead of multiplying by e to the j omega naught n, if we multiply by some constant, some complex quantity z0 to the power n, let's see what happens. If your x of n is the pair of capital X sub z, then x of n, z to the n, z0 to the n, z0 is a constant, shall be in general capital X of z over z0. It's very simple to prove this, because z0 to the power n comes, and z0 x of n, z to the minus n, z0 to the n, z0 to the n can be written as z0 to the minus 1 whole to the minus n, and that's how divided by z0 comes. Now z0 is in general a complex quantity. It's not necessarily an exponential. z0 could be of the form r0 e to the power j omega naught, and therefore it's not simple rotation. The ROC now is changed. In other words, if the ROC of capital X sub z be r, then the ROC of this shall be
1 by mod r naught.
1 by
Mod r naught times r.
where is r naught?
That is the
R naught is this. Okay. In general we can say the ROC would be r times z naught, the ROC. Well, you multiply by r naught instead of, because the angle is not effective, it is simply multiplied by z naught. Is that okay? We can say in general the ROC is this. Now, which means that if capital X sub z, has a pole at, let's say, p, at z equal to p, then capital X of z by z naught has a pole at p times z naught. All right? Has a pole at, what does this mean? Pole at p times z naught. What is the variable? Z. At z equal to p times 0. That's all that means. In other words, the poles and zeros shall be scaled by the factor p. They shall be multiplied by the factor p. By the factor 0. Yes, that's right. I'm sorry. Then another interesting property is that of time reversal, and this is quite dissimilar to what we have learnt in either Fourier transform or Laplace transform. That is, if x of n is the pair of capital X sub z, then x of minus n is the pair of capital X of 1 over z, which can be also very easily proved, because this transform is x of minus n, z to the minus n, which I can write as x of r, z to the r, which can be written as z to the minus 1 whole to the power minus r, and therefore this is simply capital X of 1 by z. All right. This means, as far as ROC is concerned, if the ROC of this be R, then what about the ROC of this? 1 by R. That is correct. Which means that if Z naught is a point in the ROC of capital X sub Z, Z naught is in R, then 1 over Z naught shall be in ROC of X of 1 by Z. That's all it means. So they obey a reciprocal relationship. But this is quite trivial as far as proof is concerned, but one often forgets. That's about time reversal. Convolution, we have already seen that if there are two sequences x of n and h of n, then the Z transform of this is simply capital X sub Z times h of Z, where the ROCs, ROC R, if this is R1 and this is R2, then R is at least the intersection of R1 and R2. It could be larger. For example, if h of Z and x sub Z have reciprocal pairs and poles, have poles and zeros which are,
one poles of one are zeros of other.
that's right. What do you call them? What is this relationship? Poles of one are the zeros of the other. Inverse relation. That is, if x of Z and h of Z are inverse with respect to each other, except for a multiplying constant, the ROC, the new ROC could be as wide as the complete Z plane, alright, and therefore, well, just to recall, we also recall that the convolution is x of n, no, x of k, h of n minus k, where k goes from minus infinity to plus infinity, or in other words, one could have x of n minus k, h of k, summation, alright, k goes from minus infinity to plus infinity. Then we consider differentiation in the Z domain, in the frequency domain. That is, we have capital X of Z equal to summation x of n, Z to the minus n equals minus infinity to plus infinity. If I differentiate with respect to Z, then what happens inside is minus n x of n Z to the minus n minus 1, n equals minus infinity to plus infinity, and therefore we can consider this to be the Z transform of minus n x n. Well, instead of keeping a minus here, why don't you bring the minus here? Then this goes away, and we multiply by a Z to take care of Z to the minus 1 here. That is, we multiply by a Z, then this minus 1 disappears, and therefore the relationship that we have is minus Z dxz dz is the Z transform of the sequence nxn. Alright? You see, differentiation in the time domain, in the frequency domain, and multiplication by the frequency variable Z with a negative sign. It's not very easy to remember. The negative sign has to be remembered. Multiplication by Z has to be remembered, is n times x of n. What can you say about the ROC? The ROC of this is R. What is it? At least R. It could be wider, because does differentiation create extra poles and zeros? No?
Derivatives of complex functions are analytic.
Analytic, but does it create additional poles and zeros? No? At the same point, at the most. It does not create new poles and zeros, new locations, and therefore the ROC is?
The original ROC is not created, because in the original ROC it is analytic.
That's right.
Derivatives of an analytic function are analytic.
Analytic. Okay. So what it does is, in dx dz, one could create, let's say from a first order pole, one could create a second order. The order of the pole may change, but not the ROC. because of the presence of z, it might change. For example, if capital X of z is a log z, ln z, then what is this? This becomes a constant, and therefore the ROC becomes the complete S-plane. So you say at least the point at the origin has to be specially taken care of. The point at the origin, z, because there is a multiplication by z. All right. These are some fine points of z transforms, and one has to remember this. As an application of this property, let's consider finding out x of n corresponding to capital X of z. This example we had done earlier, log of 1 plus a z inverse. We shall now do this to find out x of n. We shall now do this by applying this differentiation theorem. Let's see how to do this. You know the ROC of this log of 1 plus a z inverse, if it is to be the z transform of a sequence, then it must be mod z greater than mod a. All right. So let's differentiate this. That is minus z dx dz. You get, after differentiation and multiplication by z, you get a z inverse divided by 1 plus a z inverse. And this must be, we are trying to find it out in an indirect way. We are neither doing long division nor using Cauchy's integral formula. We are doing it in an indirect way. This must be the z transform of nxn. By the theorem that we have just proved, this must be the z transform of n times xn. Now, how do we find out? How do we find out what is the inverse z of this? Now we know, we proceed step by step. We know that 1 by 1 minus a z inverse is the z transform of a to the n un. Now instead of minus a, we have a plus a here, and therefore 1 by 1 plus a z inverse is the z transform of minus a to the power n u of n. All right. Then you multiply by a, that is a by 1 plus a z inverse will be the z transform of a minus a to the power n u of n. And finally, we have to multiply by z inverse. So if I multiply by z inverse, 1 plus a to the minus n would be the whole thing shifted by one sample to the right or to the left, delayed or advanced. I multiply by z inverse, so it must be delayed, and therefore we get a minus a to the n minus 1 u of n minus 1. All right, and this must be n times x of n by the theorem, and therefore x of n must be equal to a minus a to the n minus 1 u of n minus 1 divided by n. This can be written in a slightly different form like this. Let's bring a minus a here, a minus here and a minus here. All right, then the whole thing, minus a and minus a to the power minus 1, they cancel out. All right, so the end result becomes minus a to the power n u of n minus 1 divided by n. A minus sign remains? Yes. Okay, minus a. Does it agree with the earlier derived result? We did. Log of 1 plus a z inverse, we had found out by infinite series expansion and inverting term by term. It should be the same. You see, the labor involved here is much less. We only use tables. We don't carry out any actual series expansion or inversion term by term. Let's take another example. A z inverse divided by 1 minus a z inverse whole square. And this we proceed like this. We know 1 by 1 minus a z inverse is the Z transform of a to the n un, and if I differentiate this minus z d dz of 1 by 1 minus a z inverse is simply this, a z inverse divided by 1 minus a z inverse whole squared. Therefore, this must be the Z transform of n times a to the n u of n. All right. This theorem is useful in many situations where a complicated function can be inverted without much of a problem. Exactly like Laplace transform, we have an initial value theorem here. But then you must define what is an initial value. If the sequence is of infinite dimension on either side of n equal to 0, then obviously it doesn't make sense to talk of initial value. Initial value theorem applies to a sequence x of n which is 0 for n less than 0. Then the initial value IV is simply x of 0. This is the initial value. And if x of n is 0 for n less than 0, then you notice that x of z is x of 0 plus x of 1 z to the minus 1 plus x of 2 z to the minus 2 and so on up to infinity. And it is obvious that the initial value x of 0 can be obtained from capital X of z by allowing z to go to infinity, and therefore the initial value theorem for Z transforms is limit capital X of z tends to infinity. All right. This is the initial value theorem, provided of course it is a one-sided sequence, or specifically it is a right-sided sequence. Suppose it was not a right-sided sequence, suppose it was left-sided, then the initial value theorem would have been different. That's right. Then the initial value theorem would have been x of 0 equal to limit x of z tends to 0. Tends to or equal to? One can put equal to. Why did we put a tends to here? Infinity. Because of the haziness or fuzziness associated with infinity. It's unfortunate. Let's state it again. X of 0, it is a right-sided sequence starting at n equal to 0. Limit x of z tends to infinity. A consequence of this is that if capital X of z is, let's say, pz by qz, and x of 0 is finite, if x of z is a rational function p over q, and if x of 0 is finite, then what is the conclusion?
Same degree.
Degree of p which we denote
is less than.
Degree of p and degree of q, they should be related by?
Equal.
Not necessarily. Finite may also mean 0. Less than or equal. All right. This is the consequence of the initial value theorem. Of course, if you see that the degree of p is greater than the degree of q, obviously there is a pole at z equal to 0. All right. So this is one of the consequences. And like DTFT, there is also a theorem for interpolation. Interpolation theorem is stated like this. Consider a sequence Wn which is derived from a sequence x of n by this relation, that is Wn is x of r. Please follow this carefully. If n equals kr and it is 0 otherwise. What does this mean? It means that there is a constant k, an integer constant k, and w of n is derived from x of n by ignoring some of the samples of x of n. All right. So what we do essentially, suppose k equal to 3. Suppose k equal to 3, then w of 0 shall be equal to x of 0. W of 1 is not a multiple of 3 and it is 0. W of 2 once again is 0. W of 3 is equal to x of 1. Are we ignoring some samples of x? No. What we are doing is, in between we are putting some samples. So this is indeed a process of interpolation. That is, what we are trying to do is to find out a new sequence, some of whose samples are to be created. And what do we do for creation? The safest thing is assume them to be 0. This is a process of interpolation. On the other hand, if we had an x of n and we ignored some of the intermediate samples, this would be a process of decimation. I introduced the term decimation, isn't it? Decimation. Decimation literally means dividing by a factor of 10, but in general, in electrical engineering, dividing by any factor goes by the name of decimation. Now, therefore, it is clear what this process means. And you see, if you want to find out W of z is W of 0 plus W of 1, let us take k equal to 3 once again, z to the minus 1 plus W of 2, z to the minus 2 plus W of 3, z to the minus 3, and so on. Now, in the case k equal to 3, you see W of 0 is x of 0, W of 1 is 0, 2 is 0, and this is equal to W of 3 is x of 1. So the next term becomes x of 1, z to the minus 3, next term would be x of 2, z to the minus 6, and so on, which simply means that this is capital X of not z but z cubed. And in general, it is not difficult to say that k, if k is a general quantity, then it would be simply x of z to the power k. What about the ROC? If x of z, the ROC is r, then what is the ROC of this? Pardon me?
R to the power k.
Not k. 1 by k. What does it mean? And a region of convergence, a region is a two-dimensional area. What does it mean by raising it to the power 1 by k? It simply means that if z0 is in R, then z0 to the power 1 by k shall be in the ROC of x of z to the k. Is that clear? What we mean by r to the power 1 by k is simply this: if z0 is in R, then z0 to the power 1 by k is in the ROC of W of z. This is what it means. Agree? An area or a region to the power 1 by k doesn't mean anything. The meaning in which we use it is this. If you spot a point in the region of convergence of capital X of z, that point is to be raised to the power 1 by k. Now what does this mean? z0 to the power 1 by k. What does this mean? It means if z0 is r0 e to the power j omega naught, then it simply means that the distance from the origin of the new ROC, distance from the origin of the point would be r0 to the power 1 by k, and its angle shall be reduced, angle will also be reduced by the factor k. Alright, that is all that it means. Next we consider the process of summation. Summation, that is, we have a sequence x of n and we sum it up from k equal to minus infinity to n, and we produce a new sequence y of n. X of n is the pair of capital X of z with an ROC equal to r. We want to find out what capital Y of z is and what its new ROC is. Obviously, yn minus yn minus 1. This is a very clever trick. This we have done earlier also in the treatment of, in the analysis of discrete time systems. This is equal to x of n, and one can easily see that capital Y of z, if I take the z transform of both sides, shall be simply capital X of z divided by 1 minus z inverse. What about the ROC? ROC is, it's a multiplication of two z transforms. One is capital X of z and the other is 1 by 1 minus z inverse. What is the sequence? U of n, that's right. So the ROC shall be, whenever there is a product PZ times QZ, the ROC is at least the intersection. So it is at least the intersection of R and mod Z greater than 1. That is the region outside the unit circle. It's the intersection of these two. And this brings us to the close of properties, and then you see we have a brief discussion on application of Z transform in the analysis of discrete time systems. The application aspect is very similar to the application of discrete time Fourier transform DTFT to the analysis of linear systems. In other words, what we have is, if we have a discrete time system which is characterized by h of n, obviously we assume that the system is, what do we assume? LTI. Otherwise none of these things are applicable. We assume an LTI system which is fed by a sequence x of n and the sequence at the output is y of n, then y of n is the convolution of x of n with h of n, and by the convolution theorem we have capital Y of z equal to x of z times y of, I beg your pardon, h of z, where the ROC obviously is at least the intersection of the ROC of capital X and capital H. The importance in linear system analysis is that instead of calculating the convolution in the time domain, it might be easier, many a times it is easier, to simply take the Z transform of x of n and take the Z transform of h of n, provided they are known or tabulated, alright, multiply the two and then you invert that Z transform. That is, your interest is in finding y of n, so you find out the Z inverse of h of z times x of z. I must caution you that this should not be done blindly, because the time domain sequences h of n and x of n might be so simple that it's easier to take the convolution rather than multiplying the two Z transforms and taking the inverse Z transform. In terms of computerization of linear system analysis, the convolution may be computationally much less expensive than inversion of Z transform. Inversion of Z transform requires separate kind of routines. They require a lookup table, alright. If it is a standard Z transform, they require a lookup table, and computationally one has to go back and forth. One has to retrieve a Z transform, multiply, then go and look up again if there exists an inverse transform. So computationally this procedure of inverting a Z transform may be more expensive than calculating the convolution directly in the time domain. One has to be careful. However, in simple systems, paper and pencil, it is most of the time it is easier to go to Z transform and take the inverse. Now if the system is causal, then you know that capital H of Z ROC, where shall it be? Outside, not necessarily unit circle, outside a circle. In other words, it would be a right-sided ROC. Can you say it right-sided? Well, if you think of a circular symmetry. Pardon me? Okay, outside some circle of radius a, let's say, ROC. Is the reverse true? Not necessary. Why? Because the sequence might start from n less than 0. So it's a forward statement. On the other hand, well, in addition, if the system is stable, then h of z ROC must include the unit circle, includes the unit circle, includes mod z equal to 1. Instead of writing the unit circle, we write mod z equal to 1. Alright? Is the reverse true? If the ROC includes mod z equal to 1, is it a stable system? Not necessary. What Pankaj says is correct, but it requires proof. Ask Pankaj for the proof, not me. If the system is causal as well as stable, I am only making a forward statement, very guarded in my statements. If the system is causal as well as stable, now you can make a definite statement. What is the statement? The ROC must be?
I said it starts before the unit circle.
So ROC must be outside the unit circle.
It should be outside the unit circle. Must be now.
Tell me.
Region outside
Okay,
unit circle.
ROC is mod z
Greater than
than
mod 1. Mod A where A is less than 1.
So it is at least mod z greater than equal to 1.
Okay, mod z greater than equal to 1. This is definite. It could be less than 1.
Yeah, it could be. So we can say something like mod Z greater than A where A is less than 1.
That's right. Mod z greater than mod A
Mod A
less than equal to 1. Alright? Satisfied? What is the conclusion about the location of the poles?
Inside unit circle.
Poles must be inside the unit circle. Must lie inside the unit circle. And this is the most important statement that comes out of the Z transform analysis, that if you see some poles for a physical, realizable, stable system, if you see for a physically realizable system, if you see a pole outside the unit circle, you can immediately conclude that it is unstable. Alright? So causal and stable system, causal means realizable. What does this realizability mean? Real time realizable. Alright? So causal and stable system, poles cannot lie outside the unit circle. And with this, we close our discussion today.